In question 4, we have to sketch some trigonometric curves on the same axes. Sketching basic trig functions should be something we're well practiced at by now, so you should have no problem sketching the cos graph and the sine graph and the tan graph for any particular set of values. In this case, we're plotting them between 0 and 180 degrees, and we are plotting the graphs of regular tan x and 2 cos x. Tan x does its normal job of looking like a crazy windmill, with the asymptotic line occurring at 90 degrees on the x-axis. We should indicate the asymptote by using a dashed line like so. We then have the graph of y is equal to 2 cos x, which will start at 2 on the y-axis, the regular 1 that cos normally starts at, and at 180 degrees cos has reached its minimum value of -1, which in this case, because it's 2 cos x, will be -2. The curvature then follows the typical sine and cos curvature down towards the intersection with the x-axis at 90 degrees and continuing smoothly on to the point at the end at 180, -2. With our sketch complete, we move on to part B. In part B, we have to show clearly that tan x equals 2 cos x can be rewritten in terms of sine only. To convert questions involving tan and cos into sine, it makes sense to remove the tan element as possible and replace it with coses and sines. We can do this using the identity tan x is equal to sine x over cos x. We've now eliminated one of the two unwanted trigonometric components, the tan. To remove the coses, first multiply through by cos in order to give sine equals 2 cos squared, whereupon we can then use the identity involving cos squared, which is that cos squared is equal to 1 minus sine squared. You always want to be on the lookout for cos or sine squareds in your trigonometric expressions, as they are easy to convert into the other. Finally, to finish up, we move everything to the left-hand side, which gives us 2 sine squared x plus sine x minus 2, as required by our show that. We then, in part C, have to solve the equation provided in part B, tan x equals 2 cos x, which of course we will utilize our brand new substitution to do so. By making a substitution for sine x is equal to any other letter, for example, v, we can rewrite the equation as 2v squared plus v minus 2 is equal to 0. Solving this quadratic in v provides us with two values for v, either -1 plus root 17 all divided by 4, or -1 minus root 17 all divided by 4. Since v is equal to sine x, we can then set sine x equal to both of these results. However, the second solution, 1 minus root 17 over 4, will not produce any solutions as it is less than -1, and values between only values between plus and -1 will be valid when setting them equal to sine x. Using my calculator, I can then do inverse sine of -1 plus root 17 all over 4, and that gives me an x solution of 51.3. We mustn't forget that we're solving for a range of values for x between plus 180 and 0, and therefore I need to make sure I check for other solutions to the sine function before giving my final answer. 180 minus the first solution for sine will always give a second solution for sine, which in this case is 128.7. Any further solutions to this function would be at least 360 degrees more or less than either of these two solutions, and therefore will no longer fall within our domain for x. Therefore, these are our final solutions for the value x.